Hello everyone, welcome to Griffiths Electrodynamics. This is problem 4.7 from the book. This is more of a theoretical problem. And real quick before we get started, I just want to say if you are new to my channel, welcome. Please, leave a like on the video if this video helps you out or my other videos do. Subscribe if you haven't already, and if you want early access to videos or if you want law tech solutions that you can view, then you can check out some of my membership options for my channel. But anyways, let's get on with the problem statement. So we are on 4.7, and it's asking us to show that the energy of an ideal dipole P and an electric field E is given by this expression here. So we have to remember, like an ideal dipole is just talking about we have a positive and negative charge separated by some distance d, some small distance d. Okay, so what is potential energy again? Potential energy, right, is the amount of energy with reference that some system has with reference to some reference point, some 0 point, right? We have to define a reference point for our starting potential energy to even have, to define potential energy in the first place. So we're going to define our 0 potential location as just infinity, right? So there's some electric field that's present already, and then you can imagine how much work does it take to bring in the charges plus and minus q into this field, essentially, or you can just think of the fact that it's not even the fact that we're bringing in these charges. It's the fact that there's an electric field already present. These charges exist, and because what we've learned about dipoles and how they work inside of electric fields, there's going to be forces acting on these charges. There's going to be torques acting on these charges. So these charges are going to want to twist and turn or whatever and line their dipoles with the fields and stuff. So there's some amount of potential energy stored just in the fact that there's this electric field present. And we want to show that the potential is given by this expression minus P dot E, where, as you can see, it depends on the dipole moment of our system. So just a quick diagram. I've drawn a vector from our origin of our coordinate system to minus Q here, and I'm defining that as R. Then I have our plus charge here of our dipole at a vector R plus D, because I'm defining D as this vector from minus Q to plus Q here, as just this separation vector. So this vector is just the vector addition of those two vectors, R plus D. Now, we know how the potential energy is related to the electric potential. The electric potential, of course, is the potential energy per unit charge. So if we multiply the electric potential by some charge Q, that will give us the total potential, I guess, the total potential energy. So we can write U as Q times the electric potential at this point, V at R plus D, this point, V at R plus D, minus Q times V of R, right? We're just summing up the two electric potentials multiplied by their respective charges, and that's why we get this minus sign here, because this is a minus Q. Or factored out, right? We can just factor out a Q and have V at R plus D minus V at R. Now we also know from earlier chapters in the book that the electric potential is related to the electric field via an integral expression, right? We know that the potential energy of an electric field can be given by a line integral across some path of E dot dl, but we know that the electric field in electrostatics it's path independent, or the line integral across it's conservative. If we have a conservative vector field, then the path integral is path independent. So our integral of E dot dl really just depends on the value of the function at the two endpoints. So V is equal to negative integral of E dot dl, from point A to point B. But if we multiply that by Q, then that will just also give us U, our potential energy. So that's what I wrote here, is just, this is minus E dot dl multiplied by Q. So this is another expression relating the potential to the electric field. But this is also true, right? This is basically the left-hand side of this integral expression, right? This is just saying that this integral is equal to the value of the potential function at the two endpoints, right? And that's kind of what I wrote here. So I wrote this left-hand side, Q times the difference in potential is equal to negative Q times this integral between our 2 points. Now, if we assume that our separation distance is small enough, and we're talking really small here, I mean, dipoles are pretty small, then we can assume that our electric field is just constant along our path, right? Along the path integral. So we can just pull the electric field out, the E dot portion outside of the integral, and just evaluate the integral across our infinitesimal little line path. And that's just going to end up being D, the separation vector. So what we end up getting is minus Q times E dot D, assuming a constant electric field across the dipole. Therefore, we know that Q times D, this is the dot product, but we can move the Q over to the D because Q is a scalar. So Q times D is just the dipole moment, right? That is the definition of the dipole moment given to us by this was this was like given to us earlier in chapter 3, I believe. But yes, so we can just rewrite this as minus P dot E then, which is exactly what Griffiths was wanting us to show. And I just said here that because P is equal to Q times D, then we can write our expression as minus P dot E. All right, so this is just a kind of a very simple sort of theoretical problem, just thinking through a couple things, but and making some approximations. But if you guys do have any questions, comments, or concerns, feel free to let me know in the comments below. I'll be happy to answer them. Like I said, if you're new to the channel, feel free to subscribe if you haven't already, and check out my membership options if you haven't already as well. But yeah, thank you guys for watching, and I will see you all on the next video.